Welcome back, ladies and gentlemen. And now we will begin the special session, ICEF Roadmap Project, Artificial Intelligence for the Climate Change Mitigation 2. First of all, I'd like to introduce the moderator for this session, Professor David Sandalow, ICEF Steering Committee, Inaugural Fellow, Center of Global Energy Policy, Columbia University. Co-Director, Energy and Environment, Concentration, School of International and Public Affairs, Columbia University. And now I would like to ask Professor Sandalow to moderate the session. Professor Sandalow, please take the floor.
Thank you very much. Good morning, everybody. I'm very excited about this session. We have a big team of people who have been working for a long time for this moment, and we are excited to be releasing right now the draft for comment of our Artificial Intelligence for Climate Change Mitigation Roadmap. And we have a great team to talk about it here on stage, including two of the co-authors of the roadmap. And the first co-author here is Maria Francis Carter, who is on the screen, joining us from New Mexico in the United States of America. Mariah is the co-founder of Lumora Technologies, which is an early-stage technology company. She's a data scientist with extensive experience in the energy technology software space, and was a co-author of one of our chapters, which you will hear about. Alp Küçükelbir is to my immediate left here. And Dr. Küçükelbir was a principal co-author of this roadmap, helped to write a number of different chapters in the roadmap. He's the chief scientist at Faro Labs, which is a company that does AI software for industrial processes. And then we're really delighted to have Rina Kawahata from the International Energy Agency, a top power system analyst at IEA, join us to discuss these issues as well. So that's our team. What we're going to do is three of us, the three co-authors of the roadmap who are on the stage, are going to kind of go back and forth, take turns presenting the roadmap for 25 minutes or so. Then we're going to hear some thoughts from Ms. Kawahata, and then we're going to have a little discussion and then throw it open to all of you, because we'd like to hear what you are thinking on this topic and any questions that you might have. And so with that, if you could pull up our slides. Here is the cover for the roadmap that we are releasing today. I think it is live right now on the ICEF website, and here are just some of the 26 co-authors that are involved in this topic, in this roadmap. By the way, AI is a very hot topic. I'm curious, how many people here have used ChatGPT? I'm curious. Great. How many people have used ChatGPT in the past week? Okay, so that's at least more than half the audience, for sure. How many have used ChatGPT in the past 24 hours? I'm curious. And a little bit less. And how many have used large language models other than ChatGPT? I don't want to limit it to the most famous one. Okay, so a number of people. That's worth doing, by the way. I recommend it. We can talk about that. We're going to talk about large language models. So AI is an extremely hot topic. ChatGPT was released a little bit less than 2 years ago and quickly became the most rapidly adopted product in the history of humanity. Had 100 million downloads, I think, in the first month, something, or first couple of months. And today, there's some interesting news on this. Today, people might have seen the Nobel Prizes in chemistry and physics were awarded today, and both of them had to do with AI research. So we're talking about a very hot topic. The topic of our roadmap is how can AI help reduce emissions of greenhouse gases? And so we didn't look in this roadmap about AI generally. We're looking at how AI can address issues that we're paying attention to here at ICEF. In particular, how can we reduce emissions of greenhouse gases? And actually, we released a roadmap on this last year. And this ICEF roadmap, which we released at COP28 in Dubai, got an enormous amount of attention. The authors, we were invited to speak to kind of government officials and media and conferences. And this was such a hot topic, we decided to do a second edition. And that's what we spent the last 6 months doing. And the second edition looks at the same question. How can AI help reduce emissions of greenhouse gases? We added extensive research on power demand for AI, which is a topic that's gotten a lot of attention in a number of countries, including the United States, where I live, and here in Japan. We updated all the old chapters. We added 6 new chapters. And then we also added 5 to 10 specific actionable recommendations in each chapter. We want to do more than just talk about what is happening and what could happen. We decided to really think about what do we recommend different stakeholders could do in order to maximally use AI to address climate change issues. And as I've already said, the draft for comments released today, and the final is going to be released November 15th in the Japan Pavilion at COP29. Here's a first part of our table of contents. We have background, and we have an introduction to AI and an introduction to climate change. We'll talk about these, but this roadmap is written both for people who know something about climate change and want to know more about AI, and for people who know something about AI and want to know more about climate change. And then we look at 8 different sectors and look at the opportunities for AI to help reduce emissions of greenhouse gases in each of these sectors. And then we look at cross-cutting issues, including the use of large language models broadly, government policies broadly, and then we conclude with findings and recommendations. And so the author of our Introduction to AI chapter is sitting to my left, Dr. Kucha-Kelbeer. The floor is yours, sir.
All right, thanks so much. Just going to confirm that the clicker works, so we're in business. Yeah, so it's a pleasure to be here. Good morning, and I'd like to give a very brief introduction to AI as a technology. Broadly speaking, AI is the science of making computers perform complex tasks that we typically associate with human intelligence. And AI is different than traditional software. It's a form of software. But instead of relying on explicit programming, AI leverages historical data and simulation to so-called train models and, quote, learn patterns. Both of these terms are taken from the learning and kind of human intelligence language. So modern AI has far-reaching capabilities. It has the ability to detect patterns in very complex systems. It has the ability to form predictions and forecasts. We'll talk about some of these applications in different sectors. It has the ability to optimize complex systems, some very exciting applications in the power sector and manufacturing we'll talk a little bit more about. And it has the ability to run simulations. You can think of these as answering questions like, what if we had done something a different way or another? On the right-hand side, you have the canonical news-making example of AI developed by a company in the UK called DeepMind, playing against the world leader here in the game of Go. And it was the first computer program to beat the leading grandmaster. On the next slide here, AI requires data. We've heard this time and again, but a point that we want to clarify is that such data need to be both available and accessible. Available means that whatever you are looking to apply AI to, data that pertain to that problem must be digitized and well measured. Human-written, hand-measured, Excel files, these are not really good and suitable for AI. It needs to be accessible, meaning that it's either available open source on the internet or at a cost. AI has progressed incredibly rapidly. Just the fact that more than half of you in this room have used the technology that 2 years ago maybe you had no real means of trying out in your daily lives is due to a few special factors coming together. First of all, computing costs have declined dramatically. This has been a long-term trend, but at the scale at which AI is leveraging computation, reduced costs have really been a huge factor. More data across a very large set of applications have become available and accessible. And generative AI is the kind of current recently hyped, very exciting development within AI. Large language models are an example of generative AI. And generative AI is special. In fact, it's so special that it has various considerations around how much power it requires, such that we ended up focusing a specific chapter just on this topic. And I just want to indicate that most AI systems that make forecasts for weather patterns, that optimize power over a grid, that help manufacturing run more efficiently, are all types of AI that uses quite modest amounts of energy. It is just this recent development around generative AI that requires the additional considerations that we will go into.
Then our second chapter is an introduction to climate change, and we were particularly thrilled and honored that the lead author of this chapter is Dr. Ho-Sung Lee, who I think is not here. I think he couldn't be here this morning. But Ho-Sung is a member of the ICEF steering committee, but is also the chair of the Intergovernmental Panel on Climate Change. So we were really honored that he would be the lead author of our chapter on this topic. And just to cover some points, which I think many people in this room may know, but atmospheric concentrations of heat-trapping gases are now higher than at any time in human history. And this chapter goes over basics, particularly for people who may be AI experts but don't know about climate change. And then I think these are astonishing statistics. In terms of global average temperatures, July 22nd of this year was the warmest day ever recorded. 2023 was the warmest year ever recorded by far, and the warmest 10 years ever recorded were the last 10 years. The recent heat waves, droughts, fires, floods are all consistent with scientists' predictions of the impacts of climate change. And by the way, at this moment, as people may know if you've been looking at the news, the state of Florida in my country is under a horrible hurricane, a very, very strong hurricane that accelerated faster than any hurricane in memory, largely because of warm waters in the Gulf Coast, we think. So we're seeing the impacts of climate change at this moment in a very scary way. And critically, the policies that are currently in place are not sufficient to reach the goals set forth in the Paris Agreement. The world's not on a path to meet its climate goals, as we discussed yesterday in this room. So we have 8 chapters on sectors. We're just going to talk about a few of them. And one of the authors of the power sector chapter is here with us, and that's Mariah. And Mariah, the floor is yours. We're not hearing Mariah. Try again. I don't see mute on the screen, so do we have any technical people who can help with this? What do we think? We could return?
Yeah, we could come back.
We got you.
Oh.
Hello, good to hear from you.
Good morning. All right, well, we can go ahead and cross that off the bingo card for our technical issues of the day, I guess. Good morning, everybody. Thanks so much for having me, and a special thanks to Professor Sandalow for including me in this session. As he mentioned, we spent quite a long time thinking about the relationship between the power sector and AI. It's something that's on everyone's mind and seems to be on the front page of every newspaper across the world. So it was something we had a lot of research to do and a lot of folks weigh in on. Just to provide a little bit of background on how we approach this topic, really breaking down what the relationship between AI and the power sector was, just from an emissions perspective, as that was the lens which we wanted to kind of review this. Just a very basic statistic, although it's a big one. 25% of global greenhouse gas emissions today can be related back to electricity generation in the power sector. And when we think about this going forward, although we've seen tremendous growth in the amount of renewable energy that's being deployed, wind and solar and things like that, geothermal to some extent, nuclear, other things like that. There's definitely continued growth in terms of fossil emissions, which is definitely part of the reason that we still are not yet able to meet the goals laid out in the Paris Agreement. However, because the power sector is so central to those decarbonization goals, it's very important to think about how AI can help assist that. And so there's a couple of use cases that folks around the world have already been considering and that have already had quite a lot of success. And we wanted to highlight two of them here today. The first one is optimizing the location of generation and transmission assets. So power generation around the world historically has had a lot of human influence and a lot of thought put into where it's going to go and how it should be orchestrated with the transmission and distribution system that it is in. However, all of the data that has been collected across many different parts of the power sector, especially usage and commercial and industrial use cases, has really helped identify better places for new generation to be built, not just from a location or a geographic perspective, perhaps places that have excellent exposure to wind or solar or things like that, but also how to link them in with the transmission sector as it exists today. And this has a lot of interesting ramifications in the distribution part of that as well, which we can certainly get into in Q&A. And then the second use case that we wanted to highlight is the output at solar and wind farms. A lot of the ways which solar and wind have been deployed at scale across the world have not had the luxury of thinking about those really powerful predictive algorithms that were mentioned a few minutes ago. But with the massive prevalence of that today in a lot of different parts of the power sector, we're starting to see 10 to 15 years worth of data being used to figure out the right time to turn up or turn down, if you want to think of it that way. So a lot of the predictive algorithms, sometimes sort of bucketed under machine learning, sometimes bucketed under AI, but at the end of the day, they're really powerful predictive models that rely on a lot of data. We're starting to see the benefits of those on grids across the world. However, we really see that as just the beginning. And when we looked into where AI can really assist the power sector going forward, there's a couple of use cases on the screen here, but I'd like to really drill down just for a second onto the third one, virtual power plants, and talk a little bit about that, as that's something that's really picked up steam in the last 12 months or so, and that we see an enormous amount of potential to help impact some of the more tricky areas in terms of balancing what we're seeing across different parts of the power sector, being specifically the rise of demand for the first time in 20 years, specifically in the US and Western Europe, part of which is related to AI, although other things, electric vehicles and things like that, are also contributing to it. And then starting to see some firm power being retired while more renewable power is coming online. And so virtual power plants, in the way that they're typically thought of today, really think about using those powerful predictive algorithms to aggregate and identify different opportunities for things like demand response, so-called allowing people to sort of toggle their energy use depending on dynamic prices, which the AI algorithms sort of help predict and help transmit to customers, allowing those market signals to really help determine when and where you should be deploying those power-saving technologies. So virtual power plants are a really exciting opportunity. There's a lot of work being done on this in the United States, in Europe, and other places around the world. However, it's not all easy, unfortunately. There's a number of barriers to the way that AI can interact with the power sector. The first and foremost one is the lack of well-developed models. As we heard a few minutes ago, these models are really powerful, but they require lots of well-organized, digitized data. And unfortunately, that's a bit tricky when you're thinking about the different level of technological development in different parts of the world with regards to the power sector. So metering infrastructure to actually digitize and collect customer usage records, whether they're from a retail customer or perhaps a business or an industrial consumer, those are difficult to organize and collect in one place. But without that data organized in one place, it's very difficult to develop models that can then help some of those predictive use cases that I talked about a second ago. And then just touching on the last one there as well, utility business models around the world have also had a bit of a wake-up call as demand starts to rise, and the makeup of the generation stack that they use has changed quite a bit as we've seen a massive proliferation of wind and solar. And so the way that utilities engage with that stack of generation assets and the way that they think about managing it It's also quite a big barrier to really unleashing the power of AI in order to help make the sector more stable, more reliable, and all the things that everyone from a retail consumer all the way to a politician cares about. However, one of the things that we spent quite a bit of time on, and Dr. Sandalow mentioned this earlier, is thinking about ways to recommend to policymakers and other stakeholders in this sector, ways to improve some of these problems and overcome these barriers. And I won't read off all of these, but I do want to emphasize the first one, which is really working on a set of data standards to help bring that digitization and standardization of data across many different parts of the power sector into one singular format, such that models can be trained on it and hopefully deployed against some of those decarbonization goals going forward. So I look forward to the comments and feedback in the report. There's many more recommendations than just these, but these are sort of the greatest hits, if you will. So David, back to you.
Mariah, thank you for that, and thank you so much for your great work on this roadmap. Really made a big difference. So we'll move now to a chapter on a very different topic, food systems, and we looked at how AI can help reduce emissions from the food system, which is 30% of global greenhouse gas emissions. And of course, climate change has huge impacts on the food system. AI can contribute to sustainable food systems in a number of ways. Among the areas that we point to is the use of AI already to integrate data from soil sensors and satellites to create fertilizer management plans. Fertilizer creates NOx emissions, and AI has been useful at both at coming up with fertilizer management plans that minimize NOx emissions while maximizing crop yields. And then a very different type of application is creating virtual farms to simulate different crops and weather conditions. This ability of AI to create virtual environments or digital twins is very helpful across a number of different areas. Instead of actually building a farm, you can create with data a synthetic virtual farm and test various different soil types or other types of changes that might improve agricultural practices and reduce greenhouse gas emissions. And we have a number of recommendations in this chapter. I'll just focus actually on the second one here, which is data related, just like the recommendation that Mariah focused on. And we recommend that national governments, private companies, and civil society organizations establish collaborative data ecosystems for food systems. So this is the theme we keep coming back to. You need data, and you need standardized, accessible, available data for AI. And now I'll turn it over to Alp, who wrote our chapter on manufacturing.
Sounds good. I'll go through this quite quickly. I hope that you're finding that we're highlighting a variety of applications of AI that go beyond just large language models. You've seen examples in the last two sectors around forecasting, optimization, predicting, and simulating. And so the same story is also true in manufacturing, which is considered a so-called hard-to-abate sector. Many different applications, like some that are listed on the slide right now, involve applications of AI to increase material circularity and forecast process conditions. All of these things assist with the transition in this sector. Going quickly again, of course, the barriers and risks that we highlighted in power and food are similarly represented in manufacturing. I'll highlight the second one here, that manufacturing facilities are typically very dangerous places. So there's an additional human health and safety consideration when thinking about adopting any technology. AI is no different. Each chapter includes recommendations. I'll also highlight a maybe different one here, David, that's complementary, the second recommendation, which is that private companies, which are the majority of the entities in the manufacturing world, are not quite equipped to adopt technologies like AI, among other new technologies. So we really recommend that they develop clear and accelerated processes to accelerate the adoption, at least of AI within their organizations. Back to you.
Great. Well, we also have a chapter on road transport, on aviation, on buildings, on carbon capture, and on nuclear energy. If you're interested, we welcome you downloading and reading those chapters. And then we get to our section on cross-cutting issues, one of which is large language models. And Alp turn it over to you for that one.
Sounds good. I'll go through this quickly again, but large language models relies on a branch of computer science called natural language processing. This sector of machine learning and AI is more than 70 years old, and large language models represents the most recent development here. And large language models have interesting applications for climate change mitigation. It improves the ability for folks to search and translate climate information. It's quite useful for summarization, especially if we are trying to digest a large body of potentially scientific literature, but also around at-scale monitoring of things like public sentiment. We have spent some time thinking about where large language models could be used in the future around making energy permitting faster, advancing education at scale, and really allowing for real-time insights to be generated from very large environmental data and others. Now, there are challenges with large language models. You might have heard of the so-called hallucination problem. No one, including the developers on the right-hand side, who are some of the most well-funded companies with some of the top researchers in the world, can explain how their large language models work. These are black boxes. And so the risks of working with incorrect information as a result of the output of large language models is important to consider, as well as the significant computational resources that takes to run these types of systems. So we have a set of recommendations here as well. Maybe I will highlight the second one, which is a topic that's near and dear to me, around trust. I just mentioned that large language models are black boxes. We as humans don't like to rely on things we don't understand. We like technology we can open up and tinker with and figure out what the inputs and outputs mean and how they work. And so we recommend that national governments and private companies really emphasize committing resources to trying to explain how large language models work.
We have a chapter on greenhouse gas emissions monitoring. I'm not going to say much about this, but I just want to highlight that I think AI creates the potential for a revolution in this area. Historically, greenhouse gas emissions monitoring has relied upon voluntary reporting by companies and by countries. But we now have enormous amounts of data coming off of satellites and drones and airplanes, and this data can be processed using AI tools. Without AI tools, there'd be enormously too much data to be understood. And the enormous amount of data plus these AI tools are starting to give us the opportunity, I think, to understand greenhouse gas emissions from point sources in real time in a way that we haven't had historically. And I think that can really create a revolution in terms of enforcement and in terms of policy development with respect to this topic. One area I particularly want to highlight, because I think it's so important, is materials innovation. And the picture on the right there is Thomas Edison, who invented the modern light bulb 150 years ago. When he did that, he spent months taking different filaments and running electric charges through them, and looking at how much light and heat was produced, and he finally came up with the optimum type of light bulb. Today, we can simulate 1 million of those types of interactions in a second. And that not only speeds the pace at which we can evaluate, but there's another exciting element of this, which we can get materials that don't actually exist, that might exist, put in chemical structural constraints in a program, and then see how they are projected to react. And then if it looks like they might react well, then create the material and test it. And I think this type of accelerated innovative process has enormous potential in battery chemistry, for example, in biofuels development, in the creation of super strong lightweight steel that could make a difference for vehicle lightweighting and for wind turbines and other areas. There are all kinds of areas where revolutions in research, revolutions in materials could make a big difference in the clean energy transition. And AI gives enormous opportunities to do this better. And the first mention there, summarizing and integrating thousands of research articles. I mean, I had an experience of this that some people may have had this type of experience with these tools, but somebody sent me a link, 40 different URLs on a topic that we'd been talking about, some articles they had found with 40 different URLs. And historically, I would have read through all of those, but I copy and pasted them into ChatGPT and asked ChatGPT to summarize those in 5 paragraphs. And 1 second later, ChatGPT had summarized those 40 articles in 5 paragraphs. Well, that was great for me. And of course, you have to be careful because it's not 100% right when it does this, but it's still very useful. And you can imagine if you're a material scientist and there's thousands of different articles that are out there on the web on this particular problem you're looking at, AI tools can be incredibly helpful in summarizing all those materials for you. So this is one type of application where I think AI can be used to accelerate the clean energy revolution. We have one chapter in this roadmap which is actually on adaptation, not on mitigation. AI is very helpful in helping to predict extreme weather. And we don't have time to get into it now, but we have a chapter that looks at this. If you're interested in it, I recommend looking at that. And then I just want to talk about this topic that's gotten a lot of attention in the media about data center power demand. And in 2023, roughly 1.5% of global electricity demand came from data centers. That's a little bit, by the way, about the same here in Japan, but about twice the global average in the US, China, and the EU. And that's a lot. I mean, that's important, although it's useful to contrast that to some other sectors like aluminum, which actually takes 4% of global electricity demand. Data center demand is growing fast. Goldman Sachs research projects 160% growth by 2030. There are a lot of similar estimates. Actually, one thing we do in our report, we spent some time this summer gathering all the different reports we could find on this topic. And we've got them all in the chapter, and there are a dozen, more than a dozen reports looking at projected data center demand. But one point that's really worth highlighting is that the growth in data center demand is not just coming from AI. AI is an important source, but it's not the only source of data center demand. 5G network, streaming services, social media, online gaming are all listed here. And then I'm just going to go back quickly because I want to talk about this previous slide here. Because the focus of our report is greenhouse gas emissions. And so we have a chapter that looks at the question, really how much in the way of greenhouse gas emissions currently are coming from AI. And my conclusion after getting very deep in the literature on this in the past 6 months is that AI computation is currently less than 1% and probably a lot less than 1% of global greenhouse gas emissions. But it's very likely to rise in the near term. And then in the long term, it's just very uncertain what's going to happen with respect to this. There's a lot of different factors that are at play here. We think the demand for AI is highly likely to increase very quickly. But at the same time, the efficiency of the hardware is getting better, the efficiency of the software is getting better. And happily, some of the major data center providers called hyperscalers are deeply committed to the use of clean energy. They're Google, Amazon, Microsoft, Meta, are deeply committed to the purchase of clean energy. They aren't able actually to purchase all the clean energy they want, but at least they are trying to deploy data centers with clean energy. So I think there's enormous uncertainty in how much greenhouse gas emissions actually come from AI, which is one reason that we need policy in order to affect that. And we have a chapter on policy. And we're running out of time, so I'm not going to go quickly, and I'm not going to go into this more than quickly. Just say that we look at policies that specifically address the use of AI for climate, both policies that promote the use of AI and policies that manage the risks related to AI. And we make a number of recommendations about those policies. One that I particularly want to highlight is disclosure. I think it is highly it makes a lot of sense for governments to require the disclosure of the amount of energy and the amount of greenhouse gas emissions that data centers and AI model developers are using. And with that, we will close with findings and recommendations. And the findings, I'll turn it back over to Al.
All right, I'm going to go through these very quickly. But if you're interested in the report, we go through a highlight kind of section of all of our findings. Just some highlights. AI is already making a difference in climate change mitigation. It has very significant potential going forward. There are barriers that we've highlighted around data availability, cost. There are risks of adopting AI that need to be mitigated. The emissions risk of AI is not an immediate concern right now, but there's huge uncertainty around that going forward that we're looking into, we should be aware of. And trust is an essential component in the adoption of AI if we hope for it to have the effect that we do across the various sectors. Passing it back to you for recommendations.
Great. Okay, we'll close on recommendations. So we have a number of recommendations. I'm not sure why somehow this slide got numbered 111. They're 1, 2, 3 in the report. It's our first recommendation is every organization working on climate change should consider opportunities for AI to contribute to its work. And that's worth repeating, that if you're working in the area of climate change mitigation, you should at least spend some time and figure out whether AI can help you. Every organization working on climate change should prioritize AI skills development and capacity building. And then governments, businesses, and philanthropy should fund places where AI experts and climate change experts can get together. One thing I've discovered working in this area for a while now is there are a number of climate change experts and people working in space who are interested in AI but don't know much about it. And there are a number of AI experts, people with programming expertise who are interested in climate change but don't know much about it. We need to find ways to bring these communities together in systematic ways to come up with the applications for using this very powerful tool to help fight climate change. Government should assist in the development and sharing of data for AI applications. Data is essential for AI, and governments have a role there. Companies with data sets relevant to climate change mitigation should consider sharing portions of those data sets. There was a great challenge about 5 years ago, I think. Netflix wanted to develop a better recommendation algorithm using its AI, and it anonymized its data and put it out in the public and challenged AI developers to come up with a better recommendation algorithm. And essentially, they outsourced their development, and they got a better recommendation algorithm, and they offered a prize for this. I think that's a creative way of companies sharing its data, and I think we need to come up with ways that companies that have data that are relevant to climate change mitigation will be incentivized to use them. We also recommend the development of large-scale open source foundation models for climate change. We recommend that all government agencies with responsibility for climate change should create an AI office. And by the way, this was a recommendation in our report last year, the first edition of this report, and I'm delighted that numbers of governments have done exactly this. In fact, the Biden administration put out an executive order which required all agencies in the US government to create an AI office or an AI special advisor, just what we'd recommended. And then we recommend government launch international platforms to support cooperative work on AI. And I can report that last week I was in Brazil, where the Clean Energy Ministerial and the G20 energy ministers met and are launching an international platform to work on AI and clean energy. So this type of work is underway. Government should work to accurately characterize and minimize greenhouse gas emissions from AI's infrastructure, and then we have other recommendations in the report. So to close, this is actually the 12th ICEF roadmap, we've had roadmaps on a variety of different topics you can see here. You can see it on the ICEF website. I want to thank NATO and MEDI for their great support for these ICEF roadmaps. Important people have said nice things about it, which is nice. Ho-Sung Lee has said the ICEF roadmaps provide important research on a wide range of technologies. Vaclav Smil, who is kind of a tough customer, has said that the ICEF roadmaps provide essential information on different aspects of our energy system. So we're really honored that Vaclav would say that. And please go to the ICEF roadmap website. Take a look. If you have any comments, this roadmap is open for comment until October 21st. Then we're going to huddle and finalize based upon the comments we receive and release it on November 15th. So thank you very much. And with that, we're really delighted that Kohata-san is here to offer comments from the International Energy Agency. The floor is yours.
Thank you very much, David. Hello, everybody. My name is Rena Kuahata. I work at the International Energy Agency. I also have a presentation. Yes, thank you. So it was mentioned that artificial intelligence is a hot topic, and that's when we start to get on board on the topic at the IEA. First of all, I wanted to share with you what we are doing about that topic these days. So our work on this topic has just only started this year, actually. In June this year, we launched a cross-agency initiative focusing on the implications of AI for energy and energy for AI. And our research is focused on all aspects of the energy-AI nexus, including these things, applications of AI in the energy system to improve efficiency and to reduce emissions, applications of AI to accelerate innovation and demonstration of novel energy technologies, and the energy footprint of AI and ways to meet growing electricity demand sustainably. As it was already mentioned, this is an important point by David. And this initiative will have 3 pillars. First is stakeholder consultations, including workshops and expert surveys, and a major high-level conference, which is coming up soon on the 5th of December, which will be hosted at our headquarters in Paris. And a special report will also be coming on energy and AI, which is planned for publication in the first half of 2025 next year. I am an energy analyst, but I'm actually a power system transformation energy analyst. I'm a power sector specialist. And my presentation today, after this, will focus mainly on electricity demand from AI and data centers. So, taking a look at the electricity consumption by data centers, it has increased in the recent years after this long plateau. And as of 2022, data centers have consumed approximately 300 terawatt hours of electricity globally. And this represents slightly over 1% of global electricity demand. This is more than twice the electricity consumed by electric vehicles, which is used less than 0.5% of global electricity in the same year. So data center electricity consumption is currently quite small in this context, but the growth also the growth is not so different from other expanding new technologies like EV, but the effect can be felt more acutely, especially in specific areas. Like in Ireland, for example, more than 20% of the electricity demand came from data centers in 2023. And in Singapore, data center accounted for around 7% of the national electricity use in 2020 already. So if it's a small percentage of global electricity demand, why is it so important to talk about it? Here, it's important because significant new demand growth requires new power infrastructure, and the potential growth of demand from data centers is still quite uncertain. And it's this uncertainty which is the key point. For example, here, studies for the European Union show that the share of data centers' consumption in total electricity demand in 2022 could range between 1.8 to 3.5%. In the United States, estimates range between 1.3 and 4.5% in 2022. And in China, it can range from 2 to 3%, according to our estimates based on the projections from the China State Council. And in some individual countries, the range of uncertainty is even greater. Global data center deployment trends, evolution of technology towards higher power demanding servers, and recent announcements of construction plans underline the importance of better stock taking of data centers. So improving the collection of energy consumption data of the sector is important to correctly identify past developments, and this in turn helps us to better understand future trends in order to inform the public debate more accurately. Here's another chart comparing the different estimates of future data centers and AI energy consumption. Some of these were already mentioned by David as well, but the uncertainty in projections is most notable in the case of the United States, where consulting firms, investment banks, industry analysts, and industry organizations have projected data center and AI energy use to 2030. And they forecast data centers could account for anywhere between 4 to 10% of national electricity use in 2030. And some of the analysis follow rather simplistic extrapolations and so on, so the methodology could be improved. And also some other studies that have a more bottom-up approach to assessing these things, where they have tracked the number of applications by data centers to connect. There it can also be that they are double counting as such, because they apply for multiple connection points with a bet, basically, that one will fail and the other will succeed. So these kind of issues need to be ironed out in order to improve our forecasts of the data centers in the future. I've run out of time. So in conclusion, quickly, data centers and AI present these challenges for us, but they also offer opportunities, which have been explained by Mariah earlier for the power sector, for innovation and clean energy technologies. So as we move forward, balancing these aspects will be crucial for a sustainable AI-powered future for all of us.
Well, thank you very much, Vinu. I want to see if anyone in the audience has questions or comments to bring in. Bill Spindle.
Thank you. Bill Spindle from Cipher News. You were talking about, yesterday we heard Dr. Smeal talk about one of the biggest impediments to really accelerating the energy transition is really just the challenge of physically building out a whole new system that in other transitions has taken many, many decades, if not centuries. It seems like this is probably the best shot at accelerating that. I was curious your thoughts on that, particularly because on the other side, when you talk about the uptake of some of this, we heard things like not 100% reliable black boxes, which particularly in the power sector seem to be things that would stand in the way of your average utility executive taking these up. So how fast is this stuff being taken up, and what do you think about the possibilities that this could make this transition fundamentally faster and different?
I'll start with an answer and then see if any of the other panelists have thoughts on this. First, in one respect, it's remarkable how fast this is adopted. I think I already mentioned that ChatGPT itself was the fastest adopted product in human history. When you're talking about software and networks, those can be adopted remarkably quickly. But many of the things that Václav Smil was talking about yesterday don't involve moving electrons. They involve moving molecules and cement and these types of things. And those cannot be moved as quickly. But I think AI can help. And AI can accelerate lots of things we were discussing yesterday. For example, it can accelerate the innovation process. I talked about that before, in my presentation. It can accelerate the permitting process. I know certainly in the United States, one of the barriers we have for permitting is just a lack of human capacity in some government agencies to process lots of material. AI can help with that type of thing. And AI can, for example, AI can help with renewable siting because we can use AI tools to do what's called dynamic line rating to push more electricity through electric lines, which means we don't have to build a new power plant or a new transmission line. We can take more through a current line. There's lots of ways that AI can help accelerate this transition. But it's also important, in my view, to be cautious about this because AI software is not moving, it's not actually moving things physically. It's just accelerating processes. I don't know, any others have thoughts on this? Mariah, might be harder for you to jump in. Any thoughts you wanted to add?
I do. Right. Yeah, I can share a few thoughts, and then I'll hand it over to my fellow panelists. So I really like that you mentioned at the end the challenge of putting such a black box in front of utility executives. And this is something that's extremely important to think about in terms of the barriers to actually rolling out AI for some of the more specific things it can do to help dynamic line ratings being a great example of this. But one other one that I'd like to just touch on is using energy storage and optimizing energy storage to help manage some of the intermittency issues with renewables like wind and solar. And one of the things that I've heard from a number of utility folks around the United States is one example which is the set of markets I'm most familiar with, is that removing the humans from the loop and sort of having this automated system to sort of set it and forget it and let the system sort of interact with the grid is something people are really uncomfortable with, and for good reason, right? We don't want to move fast and break things with critical infrastructure. That's a completely inappropriate approach to bring. And so I think that really figuring out sort of a stepwise approach to how you bring in the parts of AI or machine learning that are the most stable and that can have the most reliable and predictable, helpful outcomes is a really important part of what the next 12 to 24 months of this is going to look like, as we see not just big sources of demand, like data centers being a good example, start to really change the way that the grid looks. But also just bring a level of comfort to people whose job it is to provide reliable and stable electricity. And so I think it's going to be a gradual process, but figuring out what the right use cases are to start with, focusing on stability and moving forward from there is going to be really, really critical.
Other thoughts? We have a question online which I think might require our PhD computer scientist to answer here, Alp. So I'll read it.
On the question.
I'll read it to you. What is called AI for marketing purposes to me is actually a 2D Fourier transform. And yes, this can be powerful, but never can be creative. While 2 petaflops were used to simulate the first 1.5 billion years, now 400 petaflops are used to compose Beethoven's 10th Symphony. What went wrong? Generative AI is a misconception, and the reason is explained by Kurt Gödel 100 years earlier. Please comment. Thank you. Do you have any thoughts on that? And would you like to tell, if you know, those of us who aren't trained, what a 2D Fourier transform is?
Yes, I was not prepared to teach the Fourier transform today, but I'll give it a stab. Yeah, no, I need a full week to respond to that question, but I'll pick out a few things. So the comment is about the fact that electrical engineering and computer science and overall data science is a long-established field, and we are certainly in a current hype cycle around large language models. Maybe the comment I'll make here is the reason why large language models have captivated all of us here is twofold. One is the magic of a very easy-to-use interface. If you want to start using ChatGPT or any equivalent tool, you go to a browser and you start typing. That's about as little friction as you can possibly imagine to try a technology that is powerful beyond, most technologies you can try on a daily basis like that. But the second thing is what large language models are working with is language. And language captures a lot of concepts that we apply to it. And so when we think about what a large language model is doing, it's manipulating our collective knowledge that's captured in language. It's not necessarily representing the knowledge itself. And so the Fourier transform is a comment here made about how we build complex physical systems. We've developed mathematics over hundreds of years and engineering know-how to build the power system that we so rely on today. You don't need the fancy, hyped-up kind of AI to do so. We've done this with tools that we have built and really can rely on. And so those will continue to have a role, no doubt. But it is interesting to think about what this new realm of effectively massive scaled computation can do for us. And right now, what it's doing is it is helping us search better and summarize faster. And that's good. We're still assessing what the value of that is. But it also has led to discoveries in how proteins get folded, and that was awarded the Nobel Prize in chemistry, right? That's not the Nobel Prize in computer science. It's in a field. And so we're just starting to understand what the capabilities of this technology really are about.
Any other questions? Yes, sir.
Shuichi Iwata from University of Tokyo. I'm one of lovers of AI, and I'm very happy for this morning. But I'd like to ask you about the foreseeability of AI application and also ethics about the trust with respect to trust. And basic, I think, theoretical or some philosophical discussions have not yet been done intensively. And have you discussed about that kind of thing? Especially, it is very important to guide our society to a good direction. And please explain some sort of discussions you have done behind the report. Thank you very much.
Well, thank you for the comment about the foreseeability and trust in AI systems. And it's a theme that we discuss in the report, and it's extremely important. And we talk about it in a number of ways. The question we're asking in this report is, how can AI help reduce emissions of greenhouse gases? It can't do that unless people trust it, unless people trust the applications. And there's lots of forces that are leading people to mistrust AI right now, I think. And so government regulations that control bias and control other ethical issues, I think are an important part of the bigger picture of AI and relate directly to the specific question of how do you use AI to reduce greenhouse gas emissions. We have, in our government policy chapter, we have a table summarizing what different governments around the world are doing right now in terms of AI regulation broadly. And every government in the world, I don't know every government, that's not quite accurate. Many governments around the world are looking right now very intensively at how to regulate AI. And one of the things they're finding is that the lawmakers just don't have the expertise to do it. And so there's governments around the world that are just trying to better understand this technology. I think they will play a very important role in developing the trust that is needed for AI. Other thoughts?
I mean, maybe I'll just add, it's an extremely important point that you bring up, and I appreciate that you do so. I'll give an example in terms of connecting it back to data availability and accessibility. It is enormously important for us to leverage this type of technology for good. And one example of that is extreme weather prediction. The better we are at predicting, forecasting extreme weather events globally, and that's essential, the better we'll be able to adapt and try to minimize its effects. The majority of data sources used for developing such models come from the developed nations of our world. So the areas of the world that need highly accurate forecasts the most are also the regions that have the least data to feed and train these AI-based systems. So recognizing this gap and investing in plugging that gap is essential to bring a fair usage of this technology to those who need it the most. Yeah, it's a very good point.
We have only a few more minutes, Rena. I just wanted to ask, from your standpoint, where you work on power systems, are there kind of any additional considerations that we should be thinking about? Anything that we kind of, as you listen to this, that we should, as we finalize this report, any advice for us about what we should do and from the work you do?
Great, thank you. Yeah, I just wanted to perhaps add some points to what Mariah had showed before in terms of the applications in the power sector. So there, I think AI use for this spatial recognition of what's already installed as well, in addition to the future development areas, is quite useful, particularly for distributed solar PV. There, in many systems, it's already out there somewhere, and system operators don't necessarily know how much of that is installed, but they're recognizing that the impacts are felt. And so I know that AI is starting to be used for those kind of things to collect the data and to better understand where are the assets out there in the power system, not only for future considerations, but already to understand the status today. So this is also a very important point of application. And also for supporting the decision making. So this is a little bit related, I think, to a couple of the questions. How do we trust, I guess, the outcomes that are, or suggestions that are being made by AI and machine learning based systems? But there, the decision point should be, in a power sector at least, still on a human to decide whether that's a good way to go or not. But they're definitely useful. It's a useful tool to get the AI in quotes and quotes, to test many different possibilities and suggest the most likely or highest probability best outcome. And then a human being would decide, based on my experience, yes, I agree, therefore I will implement this decision in past system operation in a secure way. So there are ways, I think, to work together and make this a useful tool, I guess, to accelerate the way we are using our energy system today, power system today, to make it more efficient and to be able to make it more smarter, basically, to adapt to the changes that it's facing. Yeah.
Well, thank you. And thanks again to Medi and to NATO for supporting this work. Thanks to all of you for listening. Please join me in giving a big hand to Mariah and Alp and Rena for their work.